Hi everyone, in this video we will talk about cross-validations. We are going to start with why we need cross-validation, and we are going to talk about two types of cross-validation. One is called leave one out, one is called Kfold. So before we talk about why we need cross-validation, I want to introduce the training and testing method. So oftentimes when you have a data set, you may not use the full data to fit the model because you may want to have a training data set to train your model, and you may have the leftover part of that data as your test data so that you can actually really check the prediction power of your model. And that also brings us to training error and test error. So training error is like you train your model using the training data, and you check the model performance on the training data. So you are using the same data to train the model and check the model performance. And when you check on the model performance, you are actually getting training error. So that error is from the training data. When you feed the model with the test data, you are going to get the test error. And it is like how good the predictions are comparing with what they really are. And that gives you the test error. We often use test error to evaluate the model because training error is not very reliable because you actually picked your model and fitted the model using that same data set. And this is a graph about training and testing data, like how the prediction error changes as you change the complexity of the model. So this blue line here is showing the training sample has a prediction error that is decreasing as you increase the complexity of the model. And this red line is showing that the test error is dropping as you increase the model complexity, but it will drop until a certain point, but then it will increase. So that means you shouldn't aim for a very complicated model because that model may give you a very large prediction error. When you split the data into training data and test data, you can split it in different ways, and each way may give you a different result. And also, when you train your model, you are only using part of the data. So you are actually losing the other part of the observations that you actually collected. So that's why we need cross-validation. The first goal here is to avoid sensitivity to the test set selection. And the second goal is to train on as much data as possible. The first method we are looking at is called leave one out cross-validation. And looking at this graph here, you can think about a data set with n observations. So you are fitting the model using all the observations but except the first observation. And then you can fit your second model, like you can fit another model using all the observations but not the second observation. So you can continue and continue fitting your model on the whole data set but leave one out. So by the end, you are actually fitting n models on n different data sets. So they are actually each data set you just leave one out. That's why it is called leave one out. And by the end, you fitted n models, and n models will give you n MSEs. And the average of the MSE is called the cross-validation error. So you can check on like which model you should use by comparing like what's the cross-validation error in the end. I'll go with the model that has the smallest cross-validation error. The bad thing about leave one out cross-validation is that you get to fit n models, and if you have a very, very large data set, it will take you a very long time. So that's why Kfold cross-validation is another option. It is like you, instead of building n models, you can try to split the data into like k subsets. Instead of building n models, you can actually try to build k models. K can be 5, can be 10, can be 20. That is like how you are going to chop your data into smaller chunks. Like if you split it into 5 folds, then you are actually building 5 models. And each time you are using 4 folds to build the model. So the idea here is that you randomly divide the data into k equal-sized parts. And each time you leave out one part and you fit the model to the other k-1 parts. And you can actually get the predictions for the left out kth part. So that left out kth part is your test data set each time. So by the end, you can take the average of the mean squared error values, and that will give you the cross-validation error. So same thing, you compare the cross-validation errors and pick the one with the smallest cross-validation error. Cross-validation also works for classification. So think about logistic regression when you are actually predicting 0 or 1, no or yes. So it also works in that way only if you change the mean squared error into test error. So it is like when your response variable is just 0 values and 1 values, your prediction using a model will also be predicted 0 or 1s. So if the real response value is 0 and you predicted it to be 0, then that's a correct prediction. If you predicted it to be 1, then that's a wrong prediction. So test error is like, what is the percentage of predicting the 0 and 1s incorrectly? And in the end, you compare the average incorrect prediction and you compare which model is better.